Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone to this elite Friday morning occasion. It's a great pleasure to have Fabian Suchanek or Suchanek. I don't know how the English
I don't know either.
Pronunciation would be here. Fabian is an ex-co-worker of Georgi Kasnetsi, who is probably well known to everyone here. They work together at the Max Planck Institute, where Fabian also got his PhD. And now he's with Serge Abiteboul in Paris, continuing work on semantics, and he's going to talk about merging or aligning knowledge bases in the probabilistic framework today.
Right. Thanks for the introduction. Thanks for coming. Even though there are so many other parallel events apparently and the WWW deadline, I appreciate that a lot that you came today. I'm going to talk about our system that's called Paris. It's quite fittingly because I'm actually working in Paris. And it's about ontology alignment. So given two ontologies, how can we find the matches? This joint work with my boss, Serge Abiteboul, and my colleague, Pierre Senelard. And so we are all part of the WebDAM project at in France. This is an overview of my talk. I'm going to first introduce the problem of ontology matching, like why would we want to match ontologies and what does it mean to match ontologies. I'm going to introduce our solution to it, which is a probabilistic model. I'm going to show some experiments which show that our stuff works nicely, and then I'm going to conclude. Let's start with the ontologies. So we are in this talk concerned with RDF ontologies, that is basically graphs of entities and relationships between them. I think you should all be familiar with this. So it's basically nodes like Elvis and the guitar and the birth date and singer and person and links between them. And these things are usually called classes, like they group several similar entities, all singers, and person groups all persons. And the links are called relationships or properties. And then we have the instances, and we also have some literals that are strings and numbers and dates and kind of stuff. So these are the kind of graphs we're going to be working with in this talk. So these are called RDF ontologies, which is a little bit different from the classical OL ontology, so it's a little bit simpler. So they're literally, they serve all kinds of purposes, these ontologies, like intelligent search, maybe even in Bing, who knows, right? Question answering, machine translations, all kinds of purposes. And there are literally hundreds of ontologies on the web. So if you're familiar a little bit with the SemanticWeb or with the linking open data project, there are, I think they have 200 or 300 ontologies, like with billions of these facts or edges there. And there are Freebase, DBpedia, Yago, Uniprot, just to name a few. And it's a huge hot topic right now. Now, many of these ontologies contain similar facts and information. Consider, for example, here Yago on the left-hand side and Elvispedia on the right-hand side, and they both talk about Elvis. Okay? And they contain overlapping and complementary facts. So here you see that both talk about the class of singers, but one talks about rock singers, which is a little bit more specific than just singers. And then they both talk about the same person, about Elvis, but they have complementary information. So the right-hand side knows that Elvis is married to Priscilla, and the left-hand side knows that Elvis plays the guitar. And anything else? Yeah. And you have properties here, birth date and born or type and married to and place, and they are sometimes equivalent, but they have different names. Okay? So here it says born and here it says birth date, okay? But in principle it's the same thing. And this happens a lot on the web. Like many ontologies talk not just about Elvis, but about the same topics from Wikipedia or from IMDb or something. So there's a lot of overlap in these ontologies. The problem is that Elvis is lonely in the left ontology. Okay, so he is not married to anybody. So more seriously speaking, like if we want to ask who is the spouse of the guitar player, right, then we cannot answer this question on either one of the ontologies, because this ontology knows that Elvis is a guitar player, and this ontology knows that he's married to Priscilla. but no ontology knows that he is the guitar player who is married to Priscilla. Okay? So Elvis is lonely. Complementary information cannot be used. And the solution, of course, is an option that's not always available in the real world, is to unify the entities. So if we know that this Elvis is the same as this Elvis, then this Elvis becomes married to this Priscilla, and everybody's happy. Right? And this is basically the goal of the talk, is to merge ontologies, that is to figure out which parts of the ontology talk about the same entities. And the goal of this is to enable queries that use the complementary information and to exploit the diversity of the ontologies. To merge these two ontologies, we have to identify several things. First, the equivalent instances. So we have to figure out that this Elvis is the same as this Elvis. And this is traditionally done by a link called SameAs, which just says that these two things are the same. But it doesn't stop there. We also have to figure out that these classes are similar, but we have to be very precise. They're not exactly the same. Rock singer is not exactly the same as singer. It's just that one is more specific than the other. So this is called a subclass of the other one. Rock singer is a subclass of singer. And we'd also like to figure out that properties subsume each other. So birthday and born, at least in this sense here, are equivalent, that is, they are sub-properties of each other. But this relationship can also be asymmetric. We're later going to see an example of this. So this is the goal of the present work, to accomplish this matching. Okay, so there's lots of previous work on this. I mean, really lots. I'm just giving a brief overview here. Much of the previous work uses hard logical constraints, and this may be inadequate. For example, yeah?
Just looking at the relations you're inferring, I know we all know you're going to head in a probabilistic direction here, but are you... a subclass of seems a very rigid notion still. Like, it's two things. I mean, there's a question of whether they're likely to be a subclass of, but it's also that these two things are sort of similar subclasses, or they mostly share the same properties. If someone is an actor, they're likely to be a human, or things like that, but they might be a dog, things like that. So, I mean, I guess, are you going to cover all this kind of...
Yeah, I'm going to cover exactly this. Yeah. Thanks for making this fun.
The alternatives just seem to go in so many directions, but at the start here, you're already kind of talking about very fixed, quite stark notions.
Yeah, this is the ideal world, right? We're going to see how the real world looks after. We're going to soften it with probabilities.
Well, I guess it's is subclass of, is that even the ideal world, or are we kind of trying to import a computer science notion into this?
That's an interesting question.
Modeling in the first place.
Right. That's an interesting question. So whether this is the right model in the first place. Whether it's the right model, we don't know. It's the most prevalent model on the web.
Right.
You can argue, and people have been working on this, to make this probabilistic, or to make it fuzzy, or to attach a weight or something. Say that, look, rock singer, I mean, some rock singers, you cannot seriously call them singers anymore, right, or something, right? So there's something. Yeah, that's the problem. Right. Yeah, thanks for raising this point. So there's lots of previous work on this. I'm just pointing out a few weaknesses that some of these approaches have, and most approaches have at least one of these problems. So many use hard logical constraints. That is, they will say, for example, okay, born in is a functional relationship. We have a functional dependency, and every person goes exactly with one birth date. So if these two people share the same birth date, then it's likely that they are the same or something. But that's not how real-world ontologies work, because many of them have been assembled automatically from some sources, or they have been assembled through community work, and it's not clear whether every person has exactly one birth date. They might have none, and they might have even 2 or 3 if the extraction process didn't work. So hard logical constraints can kill the approach very quickly if there's just one thing that doesn't work out. Many of the previous approaches require parameter tuning. That is, you want to match two things, and then there is some threshold alpha, and there's a scoring function, and the 2 or 3 or 5 components of the scoring function are being added up, and there's alpha, beta, gamma, and you have to adjust the alpha, beta, gammas. And we would like to do without, if possible. Well, and last, and this is an interesting point, especially in the presence of all these large ontologies, none of these approaches has been tried on the large ontologies on the web. That is, there are different directions of research, and some work on abstract small ontologies that, like toy ontologies of a few hundred concepts, and these we don't know whether these scale to the billions of entities on the web. And then there are the big database folks who do record linkage, all this kind of stuff, but this stuff hasn't been applied either to the large ontologies. But the most important point is maybe The previous work has been focused either on instance matching or on schema alignment, but not both. That is, previous work mostly looks at matching the instances here and the literals here, one. So this is like what's traditionally done in databases, like record linking and entity deduplication, kind of stuff. Or schema alignment, which is focusing on aligning the classes and the names of the relationships. And this is traditionally done in the SemanticWeb communities and in the logic communities. But few projects have actually looked at both. Which is a pity, because obviously all these things influence each other. As soon as you know that born is the same as birth date, this will help you figure out that these two Elvises are the same. And if you know that these two Elvises are the same, then maybe this gives you hints about how the classes are related, and vice versa. So all of these interact. And the more we know here, the more we learn here, the more you learn here, the more you learn here. And so the hope is that by looking at all of these problems together, we can solve it more efficiently. And this is the approach I'm going to present today. Paris, which means the probabilistic alignment of relations, instances, and schema. Yeah, 3 wishes at once. All right. We chose a probabilistic approach. That is, we're going to model. I mean, we tried out different approaches. We tried maximum satisfiability and some cache-based model and page rank, and so we tried different things, rule-based models. But in the end, this one seemed most promising, and it has the advantage that it's not crisp. So exactly these uncertainties that we've been talking about, they can be modeled here. So we're going to model 3 probabilities. First, the probability that one class is the subclass of another class. The probability C1 is a subclass of C2. This concerns this upper layer here. The probability that 2 entities are equal, 2 instances, Elvis and Elvis, this contains this layer here. And the third probability, which is the probability that one property born is a sub-property of another one birth date here, and vice versa. So we're going to, throughout this talk, we're going to define these 3 probabilities, and once we've defined them, then we can derive, this gives us the matching. Okay. All right, let's start with the instance level here, and more precisely with the literals. Okay. So let's look at strings and numbers. In our model, we estimate the probability that 2 literals are the same upfront, simply by some kind of specified distance. For example, for strings, you can use a string distance, like a Levenstein or edit distance or something. For numbers, you can use a numeric distance, or for other literals, it can be domain-specific. For example, this is actually something we should think about. For example, the probability that 2 phone numbers are the same is actually not numeric, because it doesn't really increase and decrease, but it might be a function of how many digits are swapped or something, right? Because people, when they write them down, they swap the digits or something. So it can be a domain-specific distance, and we use a very simple approach. We estimate the probability that 2 literals are the same simply by the identity function. So if the 2 literals are identical, we say the probability that they are the same is 1, and otherwise the probability that they are the same is 0. Okay. This is justified by the semantics that RDF ascribes to literals, that literals represent themselves in the universe. So they are always themselves. If I know the literal, it's not an identifier for something, but it is the very same thing. So if the 2 things are syntactically equal, they are also semantically equal. And this is what we use here. It's a very simple string distance.
But that sort of assumes that the same sort of concept is represented in the same way across different ontologies.
Yes. Yeah, this is the hypothesis, that for literals, the same concept is represented the same way across different ontologies. Exactly. So this is enforced by the RDF semantics, which has a whole data type hierarchy for literals. And so the hope is that this works out. Yeah?
So how much harder will everything else become if you change this assumption? I mean, because this assumption isn't going to be valid like for a whole bunch of uses of literals, so how crucial is it?
Yeah, so we tried different string distances, and the only thing that we need for this to work is that we have something to bootstrap the system. And we choose to bootstrap on the literals, and whether you bootstrap with 1 or 0 or something else, it just has to be some value, something that can get the system up in the beginning. So whether this is 1 or 0, or whether this is another numeric value, is not so important, as long as you have something from which you can start.
Mm-hmm. So it would be fair to say that that's actually just the initialization of an estimate, right? Because that
yeah.
number, once the system has run, then that number wouldn't be 0 or 1, or would it?
It would always, since we fix it up front and we never change it, it's not an it's an upfront estimation, but we never undo it. So we say literals are the same or they're not the same. No.
So it's 1935, and are these two dates the same?
Yeah, exactly. So this is a very bad example here. So for our approach, they're not.
Yeah.
Okay. I mean, it's fine if that's what you need to do. Yeah, go, that's fine. Yeah.
Okay. Thank you. All right. So this literals, and this was supposed to be the easy part of the uncontroversial part of the system. Now let's go to the controversial part of the system. Now let's look at the instances. So Elvis and Elvis, are these two the same? Now here I changed the example. Are these two the same? And for the instances, the relations give a hint. For example, not many people are called Elvis. So if these two are called Elvis, then this is highly indicative. It gives us a very strong hint that the two are the same. By contrast, the two are also born in 1935, but that doesn't mean anything. Many people are born in 1935, it doesn't make them the same.
My father was born in 1935.
For example, yeah. For example.
Elvis?
What's it called?
No, well, not that I know. But maybe Elvis is alive and has a son.
Yeah, we're going to figure that out.
Germany.
Right. So we need to distinguish somehow between the label, which carries a very strong indicative meaning, and between the birth date, which doesn't contribute so much. I mean, maybe if it's up to the day, then maybe it contributes something. But if it's just the year, less. How do we measure this? And we use the functionality, the inverse functionality. That is, we measure how many incoming links one such literal or entity has. So, for example, for label, I think I have an example here. Yeah, there is only one person called Elvis. So in each ontology, we look at this separately in each ontology. So we take all the incoming label links of Elvis Presley, and we take 1 over the number of incoming links. One person called Elvis Presley. That's the inverse functionality of label Elvis is 1. But there are many people called many people born in 1935. So the inverse functionality of born is born in this year is say 1 over 10 because there are 10 incoming links here.
So the incoming links would all have to be of the relation type.
Yeah, exactly. So, and then we generalize this. We go from, I mean, we first tried, and this is actually interesting. So this is something we discussed. So how indicative is it, and does it depend on the actual instance here? And maybe for the birth year it does not, but for the country it does, for example. So if you know that Tor and I were both German, then that doesn't make us the same. But if you know that Tor and I were both citizens of Liechtenstein, for example, right, which had like 4,000 inhabitants or something, then, I mean, the probability increases slightly, right? So it might also depend on this value here, okay? But we chose to walk over this and ignore this for the reason that the ontologies are often very incomplete, and especially Iago, for example, has maybe 2 citizens of Liechtenstein, and it would immediately make them the same. So this is why we chose to walk over this.
Well, just to make this clear, so essentially you're sort of, you normalize by the number of instances in the ontology that you, essentially your ontologies are your universe.
Yes,
right?
exactly.
Yeah.
Exactly. Yeah, so it gets biased very quickly to particular instances, which is why we averaged out the inverse functionalities. We define the inverse functionality of a relation as the harmonic mean over all the inverse functionalities for all entities here. So we count not just for Elvis Presley the functionality, and for Madonna, and for Priscilla, and for everybody, and we take the harmonic mean, which gives us an indication of how specific, how indicative one relationship is. So the inverse functionality of label is going to be very high. This is a guessed value, because most people have distinct names, whereas the birth year will have a very low inverse functionality, because most people, or many people, share a birth year. Okay. Now comes the controversial part, okay? The probabilistic part.
So are you moving away from this slide?
Yes.
So I didn't quite understand. So the harmonic mean is taken over Y, and Y is an instance.
Is the Elvis Presleys and the birth years. So we are looking for a relationship R, which goes to which is targeted to, which has a source and a target, and we are averaging. So we are computing for one target the inverse functionality, average with the inverse functionality for another target, average with the inverse functionality for another target, averaging over these. Yeah?
Do you only use the targets, not the sources?
This is going to be the functionality. So we talk about inverse functionality and functionality. So right now we're only looking at the targets because this is a very intricate thing. So only if this, it works only in one direction. So look here, for example, born. The fact that these two Elvises are born in the same year doesn't mean anything because here there are many incoming links. So this is a very popular thing. Whereas Elvis himself has only one birth date. But the fact that what I want to measure is how indicative is that these two share their target. This is why I'm talking about the target. I'm going to talk about the functionalities later. So it works in both directions actually. Now, please sit comfortably in your chair. Now comes the probabilistic part. So, x and y, x and x prime shall be matched. X and x prime shall be matched. If there exists one target here that they both share, and the relationship has a high inverse functionality. Okay? So meaning if they both share, for example, their birthday, we don't do anything. If they both share their passport number or their email address or their name, then we're going to match them. Okay? Because this is, like my passport number is something that is unique to me. Nobody else has the passport number. So if the two people have the same passport number, they must be the same. Same with email addresses, kind of stuff. Okay? Okay? Now, this can be transformed as this. So you simply negate here, and then you say, if there exists something, then it's not the case that for all this doesn't hold. Okay, this is simply negated. Now, since this is basically a universal quantification over all the targets and the relation with these properties, we can as well see this as a big conjunction over all these things. So it holds for all these. That means it's holds for the first and for the second and for the third and so on. Okay. It's one big conjunction. Okay. Look how nicely my my slide editor renders the LaTeX stuff. Yeah? Very nice. Now, now let's compute the probability of this happening. What is the probability that we match x and x prime? What is the probability that this happens? The probability that this happens is PR of this stuff. Okay. Okay. So far nothing happened, but now it happens because now we need very adventurous independence assumptions, which go here. And then under these independence assumptions, this is this. Why is this? It is this because we have the negation of something, which is 1 minus, and then we have a big conjunction. And the big conjunction, if all the probabilities are independent, is a big product. It goes here. Then we have negation, which is 1 minus, and the probability that this happens is the probability that this happens. And now we cheat a bit. We say the probability, we understand this as an event, that this function is inverse functional, yes or no, and the probability of this happening is estimated exactly by the inverse functionality. Okay, this is where we cheat a little bit. But the rest is basically given by the independence assumption that makes you walk from here to here. And once you've walked here, this is exactly the probability that you should match x and x prime. This is the controversial part.
So how do you interpret this probability then? Because it just follows from your assumptions, but there's not really a model yet.
Right. So this is inside our world. And in our world, two things are equal if they share one inverse functional argument. And then the probability of this is the probability of this. So intuitively, this works very easily because I'm going to go on this on the next slide. Why intuitively this makes sense. Now from the model, it works only under these strict under these independence assumptions. And then the idea is if these hold, if these held, right? And then if you do this 1,000 times, then this is going to estimate the probability that two things are the same.
So are you saying, so if you had one relation that is an inverse functionality and you knew that with 100% certainty,
yes,
then you would match them in a deterministic fashion?
Yes, exactly.
Now you're saying I'm not quite sure if I have such a thing, but this looks a bit like one, and that looks a bit like one. So one of them might be one, and that's how the probabilistic reasoning then, yeah.
Exactly. This is the ideal world, right, where everything is independent. And then this model is indeed the probability that I should match the two. Now, intuitively, this thing, this is the same formula, evaluates to 1 exactly if I have one inverse function relationship, label, and the two targets match, Elvis, Elvis, Presley match, so this is 1, this is 1. If this is 1, this is 1, 1 minus 1 is 0. And as soon as you have in the product 1, 0 here, that is, this product is going to run over the Elvis Presley's and about the birth date. And as soon as you have one inverse function relationship and the targets match, this is going to be 0. So the whole product, as soon as you find 1, is going to be 0. And the 1 minus 0 is 1, so then the two are matched. So intuitively, this smoothens very neatly the crisp case where we have one inverse function relationship and we know they're equal. In this case, okay. But what if this, we don't strictly know whether they're equal? So in Elvis Presley is literal, so they are equal. But what if they are both married to Priscilla, for example, and we don't know whether the two Priscillas are equal? Then we need to smoothen somehow. And this model does exactly all the cases in between. So between the crisp case where we know they're equal and the crisp case we know they're not equal. And this model is correct for these two cases, and it does something smooth in between.
Okay. Make a comment. So one could imagine a case where there's two of these relationships, both of them have them. Say it could be the first half of the passport ID and the second.
Okay.
And then, really, if you reasoned correctly, you would arrive at a probability 1 that they're the same under your assumption, if you just lump the two together. But this model will kind of estimate for each one of them the inverse, how do you call it? Inverse
functionality?
Functionality, exactly. And then will not arrive at 1. Right? It will then kind of have a product of the two probabilities.
Yeah, if you're saying that each ontology has half of the passport ID?
No, each ontology has, each of these items has two of these, has both.
Yeah.
Has separate relations.
And
so
do they have different
lump
names
them
or not?
together, if we concatenate them, we would have easy exact match.
Yeah.
But they're split in the middle.
Yeah.
So we need two items to exactly
Yeah.
identify. And I'm wondering how this would cope with that case. And I think it would smoothen it too much.
It might
arrive at the fact that you can actually now do exactly.
It depends on whether you have two different relationships or not. Are they the same relationship or not? The one that you use to connect the two passport
I thought
halves.
they were different. One
different.
is the
okay.
first half of the passport ID and the second half of your
So in this case, we're going to be smooth because the problem is that 2 or 3 people might share the first passport half.
Yeah.
And this is going to smoothen it. Because this works only under these adventurous independence assumptions here. And this means that we are only looking at particular relationships. Of course, if you take, I'm going to give you a different example, which is more semantic than, a little bit more semantic than the one you're saying. If I have only the birth date, then it doesn't tell me much. If I have the birthplace, doesn't tell me much. If I have the first name, doesn't tell me much. If I have the family name, doesn't tell me much. But altogether, of course, they do determine that they're the same. And this is what the model doesn't see. Because the model sees just the same thing. Up to now, the model doesn't see it. Because through this product here, it does add up. So if you have many different things, like 10 different things which are per se not very indicative, the model sums them up and it does make a difference. So in the end, it does.
Yeah, so it accumulates the evidence, but not maybe as crisply as one might.
Exactly.
Yeah.
Exactly. There was another question.
So does it mean that the quality of match will depend how you sort of partition the relationships up? So in one database, if the name, first name and surname are concatenated, but in another database, the first name and last name is separate.
That's a good example.
Yeah, that's exactly the example that Konstantina is running into, and then doesn't work. So it will not find, if you have Elvis here and Presley here, and if you have Elvis Presley here, it will not find the matches. It will not be able to figure out. This is what we call a structural difference, and structural difference is actually something that we have not dealt with, and we don't know any product that can deal with it because it generalizes. It's not just here I have label Elvis Presley and here I have Elvis and Presley. It generalizes. For example, you can have here that Elvis is born in 1935, and I can have another ontology where Elvis is in the class of people who are born in 1935. So here it's a class and there's an entity. Or you can have here Elvis has gender male, or Elvis is in the class of male people. And there's one more thing. Or Elvis has gender male, or Elvis is male true. Okay, so there in these ontologies there are three different ways to model things, either by binary properties, either by classes, or by properties, or by attributes with a true-false value. We can twist stuff into these things. And if you have such a structural difference, and the one that you're mentioning falls into this, then it doesn't work. In last case, if I have here born in the UK, and here born in Cambridge, which is located in the UK, likewise doesn't work. So there has to be structural similarity up front. Otherwise, this thing doesn't. So this is a future work to deal with if the structure of the other thing is different. Yeah?
Names of the labels should have to be exactly matching, right?
No. Right now, for this example, they do. But on the next slide, we're going to talk about what happens if they don't. Yeah? We go on? Actually, in 2 more slides. Because there's one case that we need to guard against. Yeah, here. So this is a recursive, of course. So this refers, in order to match these, we need to know whether these are the same. And for literals, this is trivial. But these might be like, both are married to Priscilla. We need to know whether the Priscillas are the same. This is recursive then. It's a big recursive thing. And this is why we need to bootstrap from the literals. Okay, how do we guard against inequalities? So Elvis is very afraid of being matched with this Elvis, because then he would be married to this lady. Yeah. So there is a severe problem here that we need to guard against. So what prevents us from matching these two people? And both are called Elvis questions because this is an Elvis imitator, like he spends his life imitating Elvis. So what prevents us from unifying these two? And it is the fact that they're born in different years. Look. They cannot be equal because they have a different value for a functional relationship. And now the functionality comes into it. This was inverse functional. That is, one person can have multiple names, but the same name is only shared by one person, like simplifying a little bit. But this is functional. That is, many people can be born in the same year. Well, one person is only born in 1 year. Which means that if we want to match the two, everybody's born in 1 year, this person will be born in 2 years, and that's not good. And here the functionality comes into play. That is, now we are guarding against matching two equally. And we do this by defining the functionality analogously to the inverse functionality. That is, we count for everybody in how many places are you born, on how many dates are you born, and so on, and we average it out. This is the functionality. It should be born here, not born in. Okay. And then we can factor it in just in a manner that is similar to the one on that I showed before, by adding this huge thing there. And this huge thing basically makes sure that for every target here, there is at least one equivalent target here. So to make this more clear, here's an example. So suppose that these two people sang different songs. So Elvis sang All Shook Up and Jailhouse Rock, and this guy sang Lavender Blue and Twinkle Twinkle Little Star. Okay. Then we want, now ignore the birth date for a second. We want this to go to 0, and the official argument is the one like the probability of, and then we transform the logical formula for everybody here, there has to be somebody there. So it's the same argument which leads to this formula. Now I'm just giving the intuitive argument. We're basically imposing that everybody here, every target here, should have a counterpart here. So for everybody here, we run through all these guys. This is this part. So for everybody here, this goes here, and this goes here. And we say, you are unequal, and you are unequal. So 1, 1, oh, you are all unequal. That means you are 1. And the relationship is functional. Now let's simplify a bit. 1 minus 1 is 0. That is, as soon as we find one relationship that is functional, and that where the targets just don't match in any way, then this factor is going to kill our probability and going to set it to 0. So this is the intuitive argument, and the official argument is similar to the one that we saw before. It's like a big transformation of logical formulas under very adventurous and independent assumptions to this probabilistic estimate. In practice, it doesn't make much of a difference. So in practice, we do without this factor. So we ran experiments with and without, but basically it just complicates matters needlessly, and it doesn't It doesn't help much. We didn't get many false matches more if we leave this factor away, so we leave it away. This is just to be complete, to show also that the functionality can play a role. Functionality helps to distinguish, and inverse functionality helps to identify. Great. Let's move to classes. Here's the class of rock singers. Here's the class of singers. And obviously, rock singer should be a subclass of singer, because here, every rock singer is a singer. So everybody who is in this set is in this set, which makes this class a subclass of this class. The ideal case. Now, that is what we would like to estimate is the probability that this class is a subclass of this class should be proportional to the size of the intersection over the size of this class. If everybody here is there, this is going to be 1. And if 90% of these are here, then this is going to be 90%. This goes exactly in the direction you've been mentioning before, because we have a notion of a soft subclass of. It's not strict. So even if we have like 100 people here who are singers, then we have 2 that are not, then it's still going to work out. Now the problem is, how do we count the number of elements in the intersection? So this here, because how do we know whether you are here? We don't know whether you are here because we only know that you match to somebody here. And you might even match to multiple people here, right? And so we don't, and then you match with a certain degree, so you match with a certain probability. So how do we count the intersection? It's not trivial. And here we use the same trick that we used before. We basically count for everybody here for all x in C, walk over this here, and we add up the probability that you are also there. Which means we add up the probability that there exists a y here that is in this class and that you are equal to. So for everybody here, we're going to ask, do you have a counterpart? Do you have a counterpart? Do you have a counterpart? And we add up the probability that these have a counterpart in order to estimate the expected sum of people who are also there. Are people taking notes? Very good. Yeah.
So the model does allow for 2 classes to be subclasses of each other, basically.
Yeah, exactly. You can go in both directions, exactly. Right. So this is basically under advantageous independence assumption, the expected number of people here who are also there, simply by summing up the probability that everybody has a counterpart. And now we use the same trick that we did before. We can express this as this simply by negating. And then we have 1 minus, and then the independence assumptions make a big product, and this gives you this. It's the same trick as before. So basically, by computing this thing, we estimate the probability that one is a subclass of the other. Yeah. It doesn't become nicer now, because now we move over to relations. If every pair of one relationship is a pair of another relationship, then the first is a sub-property of the second. So Elvis is married to Priscilla, and Elvis knows Priscilla and Elvis knows Madonna. Both had an overlap of 7 years. I don't know whether they actually got to know each other. I mean, after Elvis disappeared, but we don't know, maybe. Anyway, so it means married to should be a sub-property of knows. And here we see the asymmetry. And the asymmetry is actually something that happens in the real-life ontologies, especially with Yago and DBpedia, we're going to see this later, where one relationship is really more general than the other one. So we're going to see examples. For example, Yago knows only created. So a writer created a book, or a producer created a film, or a composer created a song. And DBpedia knows composed is author of and is producer of. So then created is truly a super relationship of all the more specific ones. Okay, so it's not real. So for now, let's just count how many people there are also there. We need to take into account, though, that there might be things in one ontology that will never appear here. So for example here, married to, and this ontology knows that these two are married, and it doesn't appear here. But we still want this to be a subrelation of this. Why? Because these two people simply don't appear here. This ontology is only about beautiful people, so it doesn't contain the two. So it just doesn't know anything about them. So what we want to do is counting all pairs here that have at least a chance of appearing here. That is, if the people appear here, then they should also be connected here. And this is what we do in a similar way to the previous one. That is, with a similar argument to the classes, we count those that are in the intersection. That is, we walk over all pairs here. Walk, 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 walk. And we check whether they are there. What does it mean, whether they are there? It means that you have a match, you have a match, and your two respective matches are linked by the node relationship. And this is what this big thing does, which can be derived according to the same argument that we saw before. And then we count those pairs here that do have a pendant at all, that do have a counterpart in the pendant, that do have a counterpart in the other ontology. So these two people, anyway, they're not appearing there. So then, of course, they are not in the relationship over there, because anyway they don't appear. Okay. And then the argument how to derive these things is the same as seen previously. And this estimates that married to a subproperty of nodes. Yeah. Okay, I see. Yeah. Okay, let's move to the fun stuff. The algorithm. Here is a very simple algorithm. We want to estimate these three probabilities in such a way that everything holds together. So because they depend recursively on each other, we just want to find the values that make everybody happy. And we chose a particularly simple approach, and we haven't done the theoretical analysis. So if you have any thoughts on this, how this could work, let us know. We do as follows. We fix the probability for literals, for x and y, as seen before, to 1 and 0. We fix the probability that certain relations are subproperties of others to a very small value initially, 0.01. It doesn't matter which value you choose, it just has to be between 0 and 1, and we ran experiments show that doesn't really affect anything.
Can you also do that for P2 being sub-relation of P1?
Yeah, for everybody. Yeah, I mean P1 can be, yeah, also, yeah, for everybody. Everybody. This is completely symmetric. Now, we use the formulas that we've seen before, and we simply iterate them. That is, from the relations we compute for the instances, from the instances back to the relations, from relations back to instances, and sometimes the literals also play a role. We simply iterate these things until convergence. And there's a little star which says, we have no proof for the convergence, but it seems to happen in practice. So this thing in all of our experiments does reach a fixed point. And we do have some intuition of why this might be the case, but we have not yet figured, we have not yet found a theoretical proof why this converges. We just don't know. Once you've done this and it did converge, then you can do, in the final step, you can compute the classes, which are again computed to the formulas that we saw before. Now, why do we compute the classes in the end and not here? It is because we found out that using the classes up front here does not help too much. So the fact that we know that both Elvises are singers does not really contribute so much. We tried at least on like 5 ontologies and never helped something. And we suspect that this might be because different ontologies have different ways of modeling classes. So as I said, some have maybe male people or something, and this does not help too much in the matching. So we found out that iterating these two things first and then computing this as a final output is the best thing. Also because the classes, as we have to say, and we're going to see later, do not match so nicely. So this works very nicely, this doesn't. So if we feed this back into here, we might just mess up stuff. So this is for us the final step. We first match everybody, and then we say, now that we know who is who, now let's look at the classes. Right, here's an example. So here's Elvis from ontology number 1, and we don't know whether he is equivalent to this person or to this person. Okay? And everybody is linked to the label Elvis. Name Elvis, label Elvis, dreams of Elvis. Okay? To whom are you equivalent? Okay? So the audience might already know the solution, but the computer does not. So suppose you also have Madonna in both ontologies, and you have the label Madonna and the label Madonna, which are trivially equivalent. And suppose, now this is like an imagined way of how the algorithm works. We observe that sometimes, but we cannot really trace it. Suppose that these share many other properties as well. They are both called Ciccone, and they are born in 1958, and they both sang the Frozen song. Then eventually the algorithm will conclude that these are so similar that these must be equal. And if these are equal, that might just tip the scale and give a little bit more weight to the equivalence that I was suspecting anyway all the time between label and name. Okay, this might just help a little bit there. Once I know that label and name is the same, it might break the tie that existed between these two. And once I know that these are the same, then it follows that That's the same. So this is how the algorithm uses different parts at the same time to walk through. Okay, we did experiments not just with the ontologies about Elvis, but with others as well. Our main experiment, which I'm going to present here, is between Yago and DBpedia, which are two of the largest ontologies on the semantic web. So DBpedia has 1.7 million instances. These are the ones in the manually refined ontology of DBpedia, 19 million facts, and Yago has 2.6 million instances and 80 million facts. This is the core part of Yago. And as you see, the ontologies are completely different. So both are derived from Wikipedia. Both have a source Wikipedia. But they are different because the class hierarchies are completely independent. So in DBpedia, they made the class hierarchy manually. They have volunteers who construct the class hierarchy. Whereas in Yago, we derive it from WordNet. Okay, so which makes the class hierarchy different. The instances overlap 50% of the instances overlap. How do we know? Because both have been derived from Wikipedia. So we have the Wikipedia identifiers, that is, we as humans can match trivially. Okay? And we hide this from Paris. And the properties are independent. So in Yago we have around 100 properties. And in DBpedia they have 1,000 properties, which are extremely specific. So here, this is joking, of course. But this is being very specific, whereas Yago is always more general. And they have complementary information. So DBpedia might think that Elvis died, whereas of course Yago contains no such rubbish. We have, for example, the gender, which is what they don't have. Okay? So it's not trivial to match the two. I mean, why not match gender with died, right? I mean, theoretically you could do that. All right.
Is the extra stuff in DBpedia is from volunteers?
No, they both base on Yago. Yeah, this is also true, actually. So they also use stuff from Yago, but they're both based on Wikipedia. So, and they have a better scraper for the info boxes, and we are stronger on the categories, which is why we have complementary stuff. Yeah. But in principle, it's two big things, and people always ask them, why don't you use us, and us, why don't you use them? So, and here we're going to see why we don't. Because
how fresh are these databases? Are they up to date?
Well, we took the first one, which is usually in the last 2 months or something. It got
and were they roughly the same day?
No, 2 months. I mean, yeah, we don't know. It might be a time frame of say 4 months or something.
Between the two. Okay.
Yeah.
Okay.
It might be there might be mismatches. Also, I mean, it doesn't perfectly match at all. I mean, at all really. The overall match of facts, I think we did for another paper. If you naively match, it's 8%. Yeah. It's not a lot.
Yeah, it's actually interesting to see how the degree of matching would change as you drifted the two apart in time to get a sense for how one way of looking at how fast they're changing in some semantic.
Yeah, absolutely. Here we just took one particular point. So here's how the stuff ran. We ran 4 iterations, and it took like around 5 hours each iteration. And we measured the change, the change in the assignments of the matches. And when it was below 1%, we stopped because we don't have any proof for conversion. So if it gets below 1%, we stop. Yeah, I know that's not nice. Now let's look here at the stuff that is nice. That precision and recall on the instances, so matching Elvis and Elvis, and we can do this. We can measure precision and recall automatically because we know the Wikipedia corresponding things. They increase both. That is. This is one example, and we are very happy about this, where actually a quite complicated model of something iterative does bring improvement. Okay, because people, including us, have often developed recursive stuff and then it improves itself and blah blah. But usually, for example, Snowball, which was the original idea of self-reinforcing information extraction, but usually after 1 or 2 iterations, you just stop it because it just gets worse, it drifts away. But this stuff really gets better, and it converges. So it really does something. So using the relations and the instances, and from the knowledge that you do it here, derive it here, and from the knowledge here, derive that one, that does improve something. So we are extremely happy about this.
You say you have the ground truth, so it's really, that's a highly inverse functionality thing, right? I mean, that's a perfect inverse functionality.
Perfect.
Thing, and you're leaving that out despite the fact that it's actually present.
Exactly. So it is hidden in the identifiers, and Paris doesn't look at all at the identifiers of entities. So if we call Elvis or 42, doesn't matter. Paris doesn't look into this. And the identifiers, they carry exactly the information. So we have a flag where you can switch it on and look at the identifiers as well, but we switch it off. So Paris just doesn't see it. Right. Matching the classes gets a precision of 74%, which is not really great, and runs roughly half of DBpedia's classes, which is also, we expected something better, so this is not extremely great. It has such a low precision because it is instance-based, and this is interesting actually. So Paris thinks, for example, that soccer players of Utah are mass murderers. Why? Because those soccer players of Utah that happen to be in Yago happen to be mass murderers in DBpedia. It's just 3 people, or 12, or 10 people, right? And since you base it only on the instances, and if you have very small classes, then stuff drifts away very quickly. Which is why we get a very steep increase in precision if you look at the threshold. So up now we don't do any thresholding, so it just runs and we take the maximal assignment. So Elvis is equal to these 10 guys, but we just look at the maximum value and we take that as the final output of the algorithm. But a class can be a subclass of multiple classes, so we can't do the trick here. So if this, I don't know which threshold this is, maybe even 0. But if you look at the probability values that we assign, then the higher the values are, the better it gets. It's just that you align fewer classes. So we do get a precision recoil curve here, but this is an inherent feature bug of the algorithm that it looks at the instance-based overlap of classes. And if the classes are very small and are semantically very specific, then it gives you the real-world overlap, which might not be the semantic overlap. Imagine if we do, for example, intersection of male and this room, then you get, yeah, this room is a subclass of male, even though we have Constantina here. Oh, why is this the case? Simply because the people that are here happen to be majority male. Okay, so we say, yeah, people at Microsoft are male, subclass of male, right? So this is not semantically equivalent, just that the instances happen the same, which is not great, but which is a very different and possibly even better approach than other approaches to matching classes, which go by the identifier of the thing. And we have at least grounding in the instances. That is, our approach will assign people here being male. Okay, all right, we make a mistake there. But since it's based on the instances, if you have larger classes and if you have more instances, then it's gonna do the right thing. So independent, while the matching of names, for example, Microsoft and male, for example, right? If you match the names, which is what other approaches do, you might get it horribly wrong. For example, Jaguar is the car and is the animal. And if you match these two because of the name, it's going to fail horribly. Whereas we look at the instances, which gives us an additional signal, which also does something wrong, but at least it's based on the instances. And if you have large enough classes, it's not going to make a mistake on large classes.
So what if you combine the both?
Yeah. Yeah. Future work. Exactly. Now, here's the stuff we are proud of. This is matching the relationships. And this is actually interesting because this hasn't been done before. There are 100 relationships in Yago and 1,000 DBpedia. And we've always been asked, like, why do you have only 100 and they have 1,000? Here is why we only have 100 in Yago. First, you see that some are really equivalent, acted in and staring, although these are inverse. So DBpedia says a movie, stars, an actor, and we say an actor acts in a movie. So we find out that these two are the same, just the inverse of each other, which is quite some beauty. Has child gets mapped to child. Here you see why DBpedia has 1,000 relationships, because they also have parent. And Yago only has child. So has child maps to the inverse of has parent. And this is, even though in DBpedia has child and has parent is not reasonably distributed. Some people have children, but these children don't have parents. So it's a mess. But in Yago, we only have has child, and through this mapping, you can actually figure out that these two are the same. So, and this is the inverse. So it's actually quite smart. Here is the super property stuff. So created, as I mentioned before, is not just writing books, but also composing pieces of music and publishing movies or whatever, or publishing papers. So we get a true superclass relationship. And then there are some spurious matches here, which is again the instance-based problem. We say that died in is a super relationship of place of burial, okay? Which is semantically wrong. Like if you die in a place, it's not necessarily that you're born there. But since Paris is instant-based and based on the true facts of stuff, most people just happen to be buried there where they are born. And so we somehow map this as like an extensional approach and not intentional, right? We map the extensional facts of the world, and we do not look into the semantic of place of birdies and that in. So we get a spurious match. So we say this is wrong. We still get a precision of 96%. So this relation alignment works very neatly, and this is something that's not trivial.
I think it would be time to wrap up.
Yeah. How about concluding?
So I guess the question is, why do you say it's wrong? I mean, why would you expect it to, in any sense, give the semantic relationships when you're just trying to work out the probabilities that, if you're a football player, then you're something or whatever, right? Why would you expect what you've done to get the semantic relationship?
Oh, we didn't expect it. No.
Right.
No.
Okay.
No, but still, it still happens to coincide. The extensional semantics, what Parrot does, happens to coincide in 96% of the cases with the intentional semantic stuff.
So,
Okay.
is
Right.
these 96%, is this now humanly labeled or labeled by you? Or
Yeah.
'cause here,
This has to be manually evaluated. So we looked at every output that Paris said, like this is this, and said yes, no, yes, no, yes, no. Okay, plus more experiments on the standard sets and IMDb. All experiments run with the same settings, no parameter tuning, no alpha, no beta, like all experiments, we have like 5 or something, all run with the same settings. Conclusion, Paris matches relations, instances, and schema holistically. Paris has no parameters to tune, no alpha. Paris shows high precision and recall, but the best of all is, of course, that Paris allows this Elvis to be unified with this Elvis, and so they can get married. And this is the happy end. Thank you for your attention.
All right, thank you. Okay, any questions?
I guess it feels like in this world that an interesting question is, if you seed the whole problem with a little bit of human-generated knowledge, crowdsourced, right, then the efficiency may be massively improved. Like, just like a couple of things like 2 Elvises, and then all the labels matching up, and then a huge number of things might flow from that very quickly. Do you know?
Oh, absolutely. I mean, there are so many additional things that you can do. So taking different distances, taking human input, taking stuff that you know up front as seeds, for example. There are certain matches on the web already.
Right.
You can take them as seeds and stuff.
Actually, do these 2 databases, don't they all store the Wikipedia, the canonical Wikipedia URL for these entities anyway, so you just could compare those to work out if they're the same?
For determining the ground truth, for the instance matching, we do that, but we hide this knowledge from Paris.
That's what you're saying?
Yeah.
Right.
So Paris doesn't know. Yeah.
I have a question. You use these probabilities, but then you present precision recall and not precision recall curves. So there must have been some kind of cutoff parameter that you chose, right? Wouldn't that be informative? I mean, if you say that something looks a bit fishy maybe in your interpretation, maybe it did have a low probability assigned to it, and so there was an indication in the system that there was something wrong?
Right. This is definitely the case for classes. So for classes, we do have this phenomenon. If you increase the threshold, then it gets better. For instances, we simply look at the maximal probability that, like I'm assigned to 10 different people, I take the one I'm maximally assigned to, and if there are ties, I just break the tie arbitrary, and I measure precision and recall. So there's no need to threshold, and we already get this precision and recall. So if you threshold, you might decrease this and increase this, but since our main selling point is without parameters, so this is just so nice, it works out this way. So
that just means fixing an existing parameter, right?
No, there is no parameter. You take the maximum. It doesn't matter which value you choose.
Oh, I see, but you could introduce one, I see. Yeah, okay. Mm-hmm. All right, other questions? Good, let's thank Fabian again. And
thank you for coming.